DARPA has always been at the forefront of artificial intelligence, driving the technology forward. So it's no surprise that we have some pretty definitive views as to where it's headed. There's been a lot of hype and bluster about AI. Talk about a singularity, that AI will exceed the capability of human beings, maybe even displace humanity. We're going to take a much more level-headed approach and attempt to demystify, talk about the technology, what it can do, what it can't do, and where it's headed. I think it's helpful to think about three waves of AI technology. The first wave was handcrafted knowledge. Here, experts took knowledge that they had about a particular domain, and they characterized it in rules that could fit in the computer, and that the computer could study the implications of those rules. Examples of this are logistics programs that do scheduling, game-playing programs like chess, or even TurboTax that you might be using to do your taxes. In the case of TurboTax, for example, you have experts who are tax lawyers, tax accountants, who are able to take the complexities of the tax code and turn them into certain rules, and the computer then is able to work through these rules. And this kind of logical reasoning is very typical of these first-wave systems. They're very good at being able to take the particular facts of a concrete situation and work through it. But they're not very good at other dimensions of intelligence. Other dimensions include, for example, the ability to perceive the outside world and see what's going on. In TurboTax, it can take your W-2 and make sense of it, but that's about the limit of it. It's also no good at learning, and learning is a major part of intelligence. And there's another characteristic of intelligence that we don't see in these first-wave systems, which is abstracting. That is, taking knowledge that they've discovered at a certain level and applying it up at another level. So what we found with these handcrafted knowledge first-wave systems is that they enable reasoning over very narrowly defined domains, but they have no learning capability and poor handling of uncertainty. But that doesn't mean that these first-wave systems are old and tedious and boring. We just had some great success this year in cybersecurity, where we had systems that were based on first-wave principles be able to study the code within a computer and be able to make sense of, here's a vulnerability, this is what I need to do to fix that vulnerability, there's something that I can do to take advantage of somebody else's vulnerability. So the Cyber Grand Challenge was a great proof that first-wave technology is still very relevant. However, first wave does stumble when it comes to the natural world. And we saw this when DARPA was doing a lot of work in self-driving cars back in 2004, 2005. We set a challenge to the community that was developing the technology for self-driving cars to say, how can you put this technology together and drive 150 miles in the desert, California and Nevada? In 2004, 0 of the cars completed. They all failed. In fact, no car went further than 8 miles down the course. And the problem was they found it very difficult in the vision systems of the car to be able to distinguish a black shape in the distance, to be able to distinguish whether it was a shadow or a rock. Should I avoid it? Should I barrel through it? And they kept making the wrong decisions. A year later, 2005, we had very many cars successful. In fact, 5 cars completed the whole course. And a big change was that they started to use machine learning. They started to use techniques that were probabilistic in the way that they handled information. And this leads us to a second wave of AI technology. This wave is characterized by statistical learning, and it's been tremendously effective in doing voice recognition on your phone, for example, or face recognition, being able to sort through all your photographs. Sometimes people say the computer will just learn things, but actually nothing could be further from the truth. There's a lot of effort goes on behind the scenes to create a system that the computer can learn in the context of. In fact, engineers take time to create statistical models that characterize the problem domain that they're trying to solve. And then what they do is they train those statistical models on specific data. The characteristics of these second-wave systems is that they're very good at being able to perceive the natural world, being able, for example, to separate one face from another or to separate a vowel sound from a different vowel sound. They're also very good at learning. By providing them with particular kinds of data sets, they're able to learn and adapt to different kinds of situations. So they're very strong in these dimensions of intelligence. However, in the reasoning, the logical reasoning intelligence that we saw was very strong with first-wave systems, the second-wave systems essentially have very limited capability. and they certainly give us no new capability to be able to abstract and take knowledge from one domain and apply it dramatically in another domain. So to characterize this current very powerful second wave technologies, we would have to say they have nuanced capabilities to classify data and even to predict the consequences of data, but they don't really have any ability to understand the context in which they're taking place, and they have minimal capability to reason. I think it's worth digging under the surface a little bit to understand a bit better why these systems work and what they're capable of doing and what they're not capable of doing. And for this, it's helpful to touch just a little bit on some higher mathematics. There's something called the manifold hypothesis. A manifold is a structure in geometry, a structure where data is grouped together to clump to form a substructure within a much larger embedding space. And it turns out that when we're dealing with the natural world, the data that we care about forms these clumps. Let me show you an example. In this rotating sphere that you see, we've taken data from a natural source and brought it down to 3 dimensions. And you can see that the different kinds of data have clumped together. Sometimes they're in stringy sort of shapes, sometimes in sort of fuzzy sponges. That red shape that you might see in the middle is actually sort of like an orange peel shaped two-dimensional thing that curves in on itself. Each of these manifolds, each of these clumps represents a different entity. And the way that an AI system will understand the data is it will separate the different clumps. Now you can imagine that it's really hard to describe one clump from another by saying, well, if it's up in the top left and shaped in this kind of set, that's very difficult in first wave technology to be able to describe. So second wave technology needs to find a new way to be able to separate these things. And what it does is it starts to take the space itself, the data space itself, and stretches it and squashes it. And here's an example. Rather than use lots of dimensions, I've reduced it to just 2 dimensions. There's a blue curve and a red curve. Each of these represents a different manifold of data, different sets of data points. And by stretching this space, squashing it and stretching it, we're able to pull these things that were intertwined, we're able to pull them apart and do a clean separation between these two. And so if you imagine that these spiral arms are clusters of data, then stretching and squashing the data space is able to separate them clearly. And this is what second wave systems do. You may have heard of neural nets. Neural nets are designed precisely to do this stretching and squashing. Now, the big secret about neural nets, they sound fancy, they sound really complicated, but the big secret about them is that they're really just spreadsheets on steroids. They're a set of layers of data computation where you start with the data at the first layer and you just move forward and do calculations, maybe 20 layers, and by the time you've come to the calculation at the end of the layer, you've now cleanly separated the data. And each of these layers of computation stretch and squash the data space in such a way that the answer at the end has the different faces, for example, separated from one another. Now, obviously, it's more complicated than I just described. There's a lot of engineering that goes into it. In particular, the computations that take place at each of these cells has to be tuned to the particular data. And that's where a lot of the skill, a lot of the energy, a lot of the capabilities come. What happens is we start out with random computations, we push the data through, we get an answer at the end, and obviously it's wrong. We look at the answer that we'd like and say, how do we adjust those data items to get a bit closer to it? Now let's do that with another piece of data, and let's work back and adjust, and we'll do it again and again, and we'll do it 50,000 times, 100,000 times. And each time we do it, we tune those parameters a little better, and it gets a little bit better at being able to separate, for example, my face from my son's face. So this kind of technology turns out to be astonishingly powerful. Even though the foundations of it are very simple, it's astonishingly powerful, and we use it a lot at DARPA. We use it, for example, to look at how cyber attacks are working through networks so that we can observe network flows in real time and at scale to be able to see where somebody is taking hold of one machine and then being able to move to another one. Another place we're using it at DARPA is to think about how to share the electromagnetic spectrum. We're all using Wi-Fi and Bluetooth and GPS and all of these things that are using radio waves. How do we effectively share that space? If my phone needs to communicate, but there's lots of other phones, how will it do it in such a way that it doesn't take away the capability of other phones to communicate? We're also combining first and second wave technologies to create very powerful platforms that cause us to reshape the way we think about the defense mission. For example, we just recently launched a new ship that's able to spend a couple of months out at sea without a human being giving it particular directions. It's able to understand what other ships are doing, it's able to navigate sea lanes, and it's able to carry out its tasks. So AI technology is just tremendously powerful. It's causing a lot of changes in the defense world and obviously in our everyday lives. But there are challenges with second wave. It's not a perfect technology. For example, if you look at this picture, here's a picture that has been classified and a caption has been generated for it. A young boy is holding a baseball bat. Now it's amusing to see something like that because no human being would ever say that. So what we find with these second wave systems is that they do tremendously well again and again and again, and then they have a bizarre example like this, and you think, where did that come from? And so these systems turn out to be statistically impressive, but individually unreliable. Here's another example. The picture on the left is that of a panda, and a vision recognition system looks at that and says, that's a panda. And then an engineer took a particular pattern of data that they reverse engineered based on the way the calculations were happening on the spreadsheet, and designed that distortion, added it to the picture. The picture on the right, to you and me, is indistinguishable. We would say that's the same picture. And yet to the same vision system, it says with 99% certainty that that's not a panda, that's a gibbon. There's also challenges with systems that are intended to learn over time. Microsoft faced this with their Twitter presence called Tay that they put up and after 24 hours had to take down. The intent of this AI bot on Twitter was that it should be able to engage in conversation with the Twitter community. But because it was actually very successful at reflecting what it was receiving, people deliberately put lots of offensive messages at it and it started to act offensively. And this one that I'm showing is actually the least offensive that I could find. And so we find this general problem that systems that are continuing to learn, we have to be very cautious about what data they get hold of because skewed training data creates maladaptation. So these challenges that we've seen with second wave, the current emphasis on AI, tells us that we need to move beyond this. We need to move beyond the simple kind of calculation that we're seeing in a spreadsheet-style calculation. And so that leads us to see that there's a need for a third wave of AI technology. And we see this third wave is about contextual adaptation. And in this world, we see that the systems themselves will over time build underlying explanatory models that allow them to characterize real-world phenomena. And I'd like to give you a couple of examples of this. So first of all, if we take just a second wave system where we're doing a lot of this calculation, perhaps it's a system that is intended to classify images, and we give it an image of a cat, and it says, that's a cat, and we say, why do you think it's a cat? The system, if it could talk, would say, well, I did my calculations, and at the end of the calculations, cat came out as highest. That's not very satisfactory. We'd much prefer the system to be able to respond to us to say, well, it has ears, it has paws, it has fur, and it has these other features. So these kinds of building the ability in these systems to understand or to have clarity about why they're making these decisions is going to be very important. But we can go further. One of the characteristics of these second wave systems is that they need a vast amount of training data. So to train, for example, handwriting recognition, you probably need to give it 50,000 examples, maybe even 100,000 examples to become pretty good at it. Now, if I had to teach my kid 50,000 times or 100,000 times how to write something, I'd pretty soon get bored. So human beings are doing something very different. We may only need one or two examples. And we're starting to see how to build systems that can be trained from one or two examples. For example, with the handwriting description, by having a model which describes how the hand moves on a page, Then when we give it a character, we can say, this is how you form a 0, this is how you form a 1, this is how you form a 2. And whenever it's then presented with a problem, like this one, how do I recognize what this character is? It would look at its various models. I have a model for a 4. How similar is that to the image I have? I have a model for a 9. How similar is that to the model I have? And it would be able to decide one way or the other which it thinks the decision is. And so these are two examples that lead us to think that the third wave of AI will be built around contextual models, where the system over time will learn about how that model should be structured. It will perceive the world in terms of that model. It will be able to use that model to reason, to be able to make decisions about things, and maybe even will start to be able to use that model to abstract, to take data further. But there's a whole lot of work to be done to be able to build these systems. So, to summarize, we see at DARPA that there have been 3 waves of AI. The first wave was handcrafted knowledge. It's still hot, it's still relevant, it's still important. The second wave, which has now become very much in the mainstream for things like face recognition, is about statistical learning, where we build systems that get trained on data. But those two systems, those two waves by themselves are not going to be sufficient. We see the need to bring them together, and so we're foreseeing a third wave around contextual adaptation. Thank you very much.